Okay, students, we will continue from where we left off previously from our first recording of the lecture. We'll be looking at section 4.2, where I think the title is to determine the order of action using the initial rates method. Okay, so this particular initial rate method actually studies how the initial rate will change when you vary the initial concentration of the reactant. Okay, so I'm going to discuss quite extensively on this using exercise 4.4 as an example, and it is very important for all of you to understand some of the concepts which I'm going to discuss over here. Okay, so I think the first thing I want to, maybe before I go into exercise 4.4, is to stress to you on how the initial rate can actually be obtained. So there are two methods where it can be obtained. Okay, so I think the first method is you obtain it from a concentration time graph. Okay, so how do you actually obtain from a concentration time graph? So for example, maybe I can go to this. So if I have the concentration of the, if let's say I measure the concentration of the reactant over time, okay, and then let's say I perform the experiment over a period of time. So I get a graph that looks something like this, for example. Okay, then what I'll do is I will draw the tangent at time equals 0. So that will look something like that. Okay, so this is what we call the initial rates. Initial rates of reaction, or we can call it the instantaneous rates at time equal to 0 seconds. Okay, yeah. So we can do it. Then so typically we begin with an initial concentration, let's say A1 for example. Okay, so we'll normally have a concentration table. Okay, then we have okay, so concentration table is moles per dm cube. Okay, then A1. Okay, then after we perform the whole experiment, so typically well, I mean, it really depends. It could take half an hour to 1 hour. So let's say we complete the experiments, then we'll draw the tangent. So we'll find the initial rates. Okay, so let's say it takes a value, let's say T1. Okay, then but this alone we can't tell much because this is just one experiment. So so experiment 1. So we need to move on to experiment 2 where we change the concentration to let's say A2, and then we get T2. Okay, then let's say from A1 to A2, right? Maybe, I mean, I'm just giving a random example. Let's say I double the concentration. Then let's say the initial rate, let's say half. Then we're looking at first order reaction because it takes twice or take half the time when the initial concentration doubles. And then from there we can determine the order of reaction. Okay, but a major drawback of this method, right, is that it's quite time consuming because for every experiment you can only get one initial rate. So normally we will not if let's say we are going to determine the order of reaction with respect to several reactants. So for example, in the case of exercise 4.4, we have 3 reactants in total, right? You notice that if let's say we are really going to go through all the 5 experiments, so it will take out a lot of time now. So normally we will go through another method known as the clock method. However, there's a slight drawback to the clock method. The clock method actually don't really measure initial rates. It measures what we call an average rate. So if I'm going to use the same example as over here, right? So I'm just going to maybe redraw the graph for you. So maybe if I'm going to use the same example over here, in this case, I'm going to use product time. Okay, so let's say the amount of product is produced over a certain period of time. Okay, so if you recall what we discussed earlier on, right, the instantaneous rate or the initial rate will be the line in green. Okay, however, in order to draw this line, we have to perform the experiment over maybe say half an hour. Of course, you don't need to complete the experiments. We can just stop the experiment maybe here if you want to. But then sometimes for new design experiments, you really don't know when you will stop. So it's a bit difficult to plan. Okay, But if we do a clock reaction, right? So what's going to happen is that which I'm going to explain a little bit more later. We are just going to allow a certain amount of product to be formed. Okay, because we can do some calculation to determine what is this amount of product to be formed. And then whatever amount of product that is formed after that, right, it will cause some changes to the color of the solution. So technically, I just need to mix two solutions, and when there's a color change, I will just stop my stopwatch, and then I will be able to determine, of course, when I stop my stopwatch, there will be a time taken where the color change first appear. But this also allows me to kind of do a back calculation so that I can find out what exactly is the amount of product that is formed, okay, over this period of time. So I can then draw a line over here in red. Okay, so in this case, what I'm getting here is what we call the average rates of production of the product. Okay, you notice that if the time is as short as possible, right, then the red line will be a good proxy to the green line. And this is the basis of clock reactions. Okay, I have an example to show you from a YouTube channel. So later I'm just going to play the video so that you have a clearer picture on what exactly is a clock reaction. But just to keep this in mind, at the back of your mind. So there are two different methods. Of course, one is faster than the other. The concentration time graph, of course, is more accurate, so-called, because you are really getting the instantaneous rate. But the clock reaction will be a good proxy. Okay, so that's something that I thought that I just want to bring to your attention. Because of course, due to limitation, it's not exactly explained entirely here. Yeah, of course, you can refer back to section 2.2. You can refer back forward to section 5.2. But if someone were to explain to you more clearly, I thought that is better. Yeah. Okay, then okay, so in this case we will use exercise 4.4 as an example. But before we move on into the nitty-gritties, right, I just want to point one important thing to you. I'm not sure whether you have noticed it. Did you actually notice that the concentration of B and C, both of them are actually way higher than that of A? So easily 50 to 100 times higher. Okay, I just want you to take note of this. I mean, in any way you want. This is done in deliberately, which I'm going to explain to you later on. But I would just want to first discuss how can we actually go about working on the first part before I move on to explain to you, because it's actually a little bit a little bit complicated. Yeah, so I thought that I just want to show you how to go about determining the order first. Then I will move in to explain to you why is it that we have to cap the some of the regions in excess. Actually, the main purpose is to make it a pseudo nth order reaction respect to A, but I don't want to go into the details before I explain how do you get the answer. Okay, so yeah, so let me just remove this first. Okay, so actually getting the order of reaction is really not difficult if you are given such a table. So I'm just going to quickly explain to you how can we actually go about getting the answer. Okay, so there are two methods that you can use to get the answers. The first method is known as inspection. Okay, inspection basically goes like this. So I'm going to use green. Okay, so it goes like this. So if you look at the first two experiments, okay, just look at the first two experiments. You notice that the concentration of B and C are kept a constant. Okay, the only thing that varies is the concentration of A actually increases 3 times. Okay, from 0.010 to 0.030. Then you notice that the initial rate actually triples as well, from 2.0 times 10 to the power minus 3 to 6.0 times 10 to the power minus 3. Yeah, so over here, right, if you want to do this question part A by inspection, all you need to do is to say something along the line that keeping the concentration of B and C a constant, okay, at 1.00 and 0.50 moles per liquid respectively, I triple the concentration of A from 0.01 to 0.03. The initial rate triples from 2.0 times 10 to the power minus 3 to 6.0 times 10 to the power minus 3. Yeah, so you notice that there is a direct proportional relationship, right? So since the increase in concentration leads to a proportional increase in the rate, so therefore the concentration, the increase in rate is directly proportional to the increase in concentration. So this is an example of first order kinetics. Okay, so this is a what we call an inspection method lah. Like you just plug some numbers and then you notice a trend. Okay, after you notice the trend, then you can say something about it. Okay, so after you say something about it, then conclude about the order. Okay, so let's try again. Let's try maybe this time around we do 3 and 4. Okay, for 3 and 4, right? You notice that the initial concentration of A is kind of constant. Initial concentration of B is kind of constant, but initial concentration of C actually doubles from 0.25 to 0.50. You notice that the initial rate remains the same. Okay, so when you're looking at this, right, what you can say is that keeping concentration of A and B a constant at 0.030 and 2.00 moles per unit respectively, when I double the concentration of C, the initial rate remains constant. So in this case, therefore, any change in concentration of C, right, will not lead to a change in initial rate. So in this case, this is typical of a zero order kinetics. Yeah. So from here you can tell that okay. So therefore the order of reaction respect to C is 0. The order of reaction respect to A is therefore 1, which is what we have concluded earlier on. Okay. Then finally, when we're trying to do by inspection, let's say we want to look at B, because we are done with A, we are done with C, now we are looking at B. Okay, so I think for B it might be a little bit simpler because in this case we kept A and C a constant. Okay, we kept them a constant at 0.03 and 0.5 respectively. But we doubled the concentration of B from 1.00 to 2.00. You notice that, okay, maybe let me erase this so that you can see it more clearly. Okay, you notice that my initial rate quadruples from 6.0 times 10 to the power minus 3 to 2.4 times 10 to the power minus 2. So it quadruples. So when I double this, this actually quadruples. Yeah, so this is typical of a second order kinetics, right? Yeah. So in this case, you say that the order of reaction respect to B is therefore 2. Okay, so what I've illustrated to you just now, although I'm just telling you verbally, because you can easily check the answer online, but I'm just telling you verbally and showcasing some of the thought process, right? What I'm just sharing with you is what we call the inspection method, where you write down what you kept as a constant and what you change, and then how the initial rate actually changes. Okay. Another method you can do is actually what we call an analytical method. Okay, maybe I should write this down. So first method is by inspection. Okay. Second method is what we call analytical method. Okay, so what exactly is the analytical method? This is basically do by math. Okay, then you'll be wondering, is there a preference between the two? Actually, there's I wouldn't have a preference, but let's say you are linguistically inclined, right? Then I think you should do the inspection method because you can write well. But if you can't really put your thoughts into writing, right, then an analytical method works. Because for an analytical method, you don't really need to write much. You just need to solve the mathematics. Okay, so I'll just give you a really simple example. So and then I think the rest you can do yourself. Okay, so I will just begin by doing this. I will begin by letting, okay, by letting the rate law. Okay, so let the rate law be, okay, rate is equals to k a to the power m, b to the power n, and c to the power of let's say q, for example. Okay, then in this case I will compare experiment 1 and 2 lah. So when I compare experiment 1 and 2, I don't need to write anything because I just need to sub in the values over here. Yeah, you notice. Okay, so so I just need to sub in the values and then solve the mathematics. Okay, so yeah, so I'm just going to copy in. So okay, so for the rate of reaction of experiment 2, right, is actually 6.0 times 10 to the power minus 3. So I will just divide it the reason why I divide is because I want to cancel off the k term lah. So divide by the initial rate for experiment 1, that's 2.0 times 10 to the power minus 3. Okay, and then okay, I'll just show you everything. I think that's easier. And then I just really just copy. Okay, so this is 0.30 m, 1.00 n, and then 0.50 q. Okay, and then k here, and then I have 0.010 m, 1.00 n, and 0.50 q. Okay, so I'm going to change to another color so that it's more visible. So you'll notice that k gets cancelled off. The concentration of B term gets cancelled off because it's the same number, and then the C1 gets cancelled off as well. Okay, and what you'll notice is that if I just simply cancel this, I will get a 3 here. Okay, and then yeah, so we'll do the same to this and we'll get a 3, but we'll do that later. Okay, so from here you get 3 is equals to 3 to the power m. Okay, so what do you notice? So this is 1, right? So therefore m is equals to 1. Okay, so what's the advantage of the analytical method? The advantage is that you don't need to write. You just need to, I mean, not saying you write. I mean, you don't need to write in words. You just need to solve the mathematics, and then you get m equals to 1, and then you're happy with that. Okay, that's really for those of you who are maybe you don't really like to write a lot. Okay, inspection method, right? You really need to be crystal clear in your writing. For example, you really have to tell, let's say 1 and 2, right? You really have to tell us that you are keeping the concentration of B and C a constant at blah blah blah, and then after that you triple the concentration, and then the initial rate triples. You know, like you have to be crystal clear. Okay. Then another reason why I can maybe share with you that the analytical method is a lot better is that because for some questions, right, they deliberately put it in such a way that there will be two concentration not being kept a constant. So they, I mean, I can't exactly pinpoint an example over here because for this particular exercise 4.4, everything is written very beautifully for you, but there are some questions that they allow you to determine the order of reaction for one, and then after that they purposely change that one and then something else as well, so that it's very difficult for you to write down verbally, if you know what I'm trying to say. So for example, maybe one experiment, right, it doubles the concentration, the rate will double, but for the other experiment, when you double the concentration, the rate quadruples, so overall the rate increases by 8 times. Then when you are putting down in words, it's very difficult for you to say stuff, right? I mean, you will say something like, oh, the quadrupling effect is due to the doubling in the concentration of this. However, the overall rate did not quadruple, it actually increased by 8 times, and then this is due to the doubling in the concentration of the other item. So when you know, I mean, I think merely by me saying that, it already confused you loads. But yeah, so imagine that you're trying to put them down in paper, right? The reader will probably get very confused. Yeah, so whenever we have this type of question, seriously, the best way is to do by mathematics so that everything else is crystal clear. Okay, yeah, so I hope I have sort of explained to you why the analytical method rocks. Okay, but of course, if you of course, simple example like 4.4, you can do inspection as well, because it might be more attainable and maybe more palatable to most of us. Okay, then okay, I'm just going to continue, and then I'm going to come back to explain to you regarding the excess concentration of BNC, because it's still at the back of my mind. I haven't really gone into that lah. Okay, then of course, the next part B is to ask you to write the rate equation for the reaction. So therefore, this particular rate equation will be rate is equals to rate constant K. Okay, A to the power 1. Oops, sorry, I think A to the power 1, and then after that B 2. So it's first order respect to A, second order respect to B. C 0 order, you don't need to put it in now. Okay, and then next you're supposed to calculate the rate constant for the reaction, including the units. Okay, so basically you choose any reaction you want. Most people will choose the first reaction because I mean it's the easiest. So I'll just write it here. So that's 2.0 times 10 to the power minus 3, and then equals to rate constant K and then 0.03 to the power 1, and then 1.00 to the power of 2. Okay, and then I solve for this. I will get the rate constant k to be 0.200. Okay, do you remember how to get the units? I think we discussed this in an earlier lecture. So if you forget, maybe I can show you once and for all. Okay, so before I write down the units, I'm going to show you how do we actually get the units. Okay, so what's the units for your initial rate of reaction? So the units for initial rate of reaction is moles per dm cube per second. Okay, and then you have an unknown k here, which you don't know the units. And then here you have concentration to the power 1 and concentration to the power 2. So on the whole, the units will be moles to the power 3 and then dm to the power minus 9. Okay, so if we do a quick cancellation, right, we're going to get a 2 here and minus 6 here. Okay, however, right, you have to move the units over just like how we normally do division. Okay, so when we move this portion to the left hand side, right, then we'll get units of k to be mole to the power minus 2, dm to the power 6, and per second. So this is your units. So make sure you write it down. Mole minus 2, dm 6 per second. Okay, yep. So this is the second time I'm showing you how to get a unit. So I hope it's clear cut for most of you, if not all of you. Okay, then calculate the initial rate for experiment 5. Okay, so I think this probably don't need me to do much. Basically, you are just going to substitute the value of k into this, and then the value of a here and the value of b here. Okay, so if you perform the correct substitution, just punch your calculator, you should be able to get 0.0500 moles per dm cube per second. Okay, yeah. So I hope by showing you how to do exercise 4.4, you are a lot clearer in how to actually go about solving this kind of problem. Yeah, but there remains one difficult part, which I kept talking about it. I kept bringing you in on why is it that we have to keep the concentration of B and C in excess, etc. Okay, I'm going to just explain to you maybe using the other PDF file. Okay, which is blank, so that's easier. So I'm going to erase this first, so that I have a lot more space for the discussion. Okay. Okay, so what I'm going to do is I'm just going to write down the concentration of A. Okay, so you notice that the concentration of B and the concentration of C, right, is in much greater quantity than the concentration of A. Okay, why is that the case? Okay, so remember earlier on, right, we let the rate law, let the rate law be rate is equals to K concentration of A to the power M, concentration of B to the power N, concentration of C to the power Q, right? Remember we did this, right? It's over here. Blah blah, where is it? Okay, it's over here. Okay, we did this earlier on, right? Okay. But little did you know that when the concentration of B and C are way greater than A, right? Okay. What we can do is we can safely assume that in the course of the reaction, right, the amount of B and C stays relatively constant. Some of you might be wondering, how can that be the case? Well, I mean, okay, so maybe let me erase this part so that it's a little bit clearer for you, and you know what to focus on. So I'm going to just highlight here. Okay, take note of the reaction. Okay, so for every 2 equivalent of A gets consumed, 2 equivalent of B will be consumed, and 1 equivalent of C will be consumed. So our focus is on experiment 1 and let's say experiment 2. Okay, actually looking at experiment 1 alone is good enough. Okay, we don't really need to look at 2. Okay, maybe I'll just erase this first. Yeah. Okay, you notice that even if all the A reacted, okay, the amount of B that changed, right, is only by 0.01. That's like 1%. And the amount of B that change is 0.005. That's like 1% as well. Do you notice that? Okay, so therefore, isn't it right to say that I can approximate the rate now to what we call K prime? Okay, A to the power M, where K prime is actually equals to K multiplied by B to the power. And this is unique to this experiment, by the way, and Q. Okay, so this is very important, and this is often the case in many of the kinetic studies. So when we do this, right, we are effectively making what we call a pseudo nth. Okay, in this case, it's not nth, it's m. Okay, order with respect to A lah. With respect to A. Then you'll be wondering, why do we need to do this? Okay, I mean, all beginning students of kinetics will ask the same question. Why is there a need to make it a pseudo nth order reaction with respect to A? Okay, the reason is this. Can you imagine the scenario, right? Can you just imagine the scenario between experiment 1 and 2 lah? If the concentration of B and C are about the same, are not very different from A, right? Okay, when I mean not very different, maybe let's say concentration 0.02 for B, let's say, I mean just a random value, and then for C, let's say 0.05, for example. Then when all the A completely reacts, right, then the amount of B that changed will be a whooping 50%. Do you notice that? Okay, then at the back of your mind, you'll be wondering change then change no difference. No, it matters a lot. Remember, at the end of the day, right, we realize that the order of reaction with respect to B is actually 2, you know. So, right, if the amount of B, if the concentration of B can change by so much, then the initial rate will also change drastically. You know what I'm trying to say? Yeah, so at the end of the day, right, when you study experiment 1 and 2, when you have B and C in relatively similar concentration to A, the initial rate will not just triple, you know. It will, I don't know what is the value to put to it. I mean, it will change, but not in a way we expected it. Yeah, so I think my point is that is when you want to study reaction kinetics, right, there is a need for us to put the reactants, right, or the reaction system in an artificial pseudo nth or nth order condition, so that we are ensured of the fact that the only thing, let's say there's a change in rate, you can be assured that the change in rate is solely due to any changes made to A, and not because B and C, in the course of reaction, the concentration decreased drastically, and their drastic decrease in concentration also caused the rate to swing to the other side. Yeah, so that is why in the design of this kind of experiments, you notice that the other reagents are often kept in excess, and the one that you are measuring, so this initial rate is likely to be maybe some color change or some change in pressure of B lah. Okay, B and C usually because they are in excess, right, and they are being consumed to give you the product, so they will not usually contaminate the solution with any colors lah. I just want you to take note of this important fact. I know at this stage, some of you might be a little bit lost. I mean, I can perfectly understand, because the pseudo nth order reaction idea, right, is not very easy to understand unless you do the experiments yourself lah. I have to admit this. Okay, so unless you perform the experiment, and then maybe as I said, kinetics is a topic that seems okay to understand at the start, but when you go on to year 2, you will experience great difficulty along the way, because you get a bit confused. Yes, so just give yourself a bit of runway to understand kinetics. Maybe a couple of months to maybe a year, and you really get clearer along the way. So I mean, just give yourself the time. Okay, so when in doubt, please do highlight to me if there's anything that you don't really understand about pseudo nth order reaction. I know it's not exactly written very clearly, or rather explicitly in the notes, but it's a concept that you have to be fully aware of. because you notice that a lot of the experiment designs are working based on that particular principle. Then another thing I know at the back of your mind, right? A lot of you might be asking, since B and C are in excess, right? Then how come the change in their concentration will affect the initial rate? Well, I mean, of course it will affect the initial rate, because when I make the excess even greater excess, right, then the probability of an effective collision will be much higher, right? So of course it will affect the rates. So I think this is not a huge surprise. So don't you think that this is really a very intelligent design in the experiment where they can kill two birds with one stone? And you notice that quite a number of our tutorial questions is really based on this understanding as well. Okay, yeah, so yeah, I do recognize that I spent a lot of time under this section 4.2 and especially using exercise 4.4, but I think it's worth the time because it represents some of the most difficult concepts to understand in reaction kinetics. Okay, yeah, so the next thing we're going to go through is we'll just finish off section 4.2 by going through the remaining lecture exercise. Okay, so now we have lecture exercise 4.5. Okay, so for part A, we have trichloromethane reacts with aqueous soda hydroxide according to the equation below. Okay, so this is an equation given to you, right? It's given over here. And then some data were recorded. So again, it's the same data, right? I mean, you can see lah. And then after that, they ask you if K is the rate constant, what is the rate equation? Okay, now I think first of all, let's just do a quick inspection. I think we'll save ourselves the details on mathematics. So you notice that when I double the concentration of trichloromethane, right? Sorry, not double, sorry. I kept the concentration of trichloromethane a constant, and I double the concentration of OH minus, the initial rate doubles. Okay, so therefore the order of reaction with respect to OH minus is actually 1. Okay, yeah. Now, you notice that between experiment 1 and 2, right, it's a bit weird because you both change. Yeah, so this is exactly what I'm talking about. Remember earlier on, I told you that this particular table given to you, everything is so nicely written. Everything is like, whenever you compare any two experiments, right, okay, I mean talking about the first 4, there will always be 2 concentration being kept a constant. So it's very easy for you to compare. For a question like this, right, you notice that they deliberately make experiment 1, right, different in concentration from the rest. Yeah, however, you can still answer it. Okay, and you notice that if I do it by inspection, it's quite difficult to actually explain. Do you notice? Okay, so let's try to do that. So maybe I'll just erase this. Okay, so let's try to do by inspection. How do we explain by inspection? Since now we know that the order of reaction with respect to OH minus is 1. Okay, so right now I double the concentration of OH minus. Okay, so I expect the initial rate to double. However, right, you notice that the initial concentration of trichloromethane is halved. Okay, then the initial rate is still the same. Yeah, so therefore, right, this doubling of the rate, right, is now offset by the halving of the rates due to halving of the initial concentration of trichloromethane. But that's quite a mouthful, right, when you try to explain. Correct? Yeah, so if you solve this by mathematics, it's very clear that the order of reaction with respect to trichloromethane is 1. So it's easier, okay, than to write out in inspection, I mean as an inspection method. But of course for MCQ, you don't really care. I mean, MCQ you don't really need to solve by mathematics, right? Because as long as you can pick your options quickly, that's what makes the difference. So therefore we pick B. Okay, but for the purpose of doing structured question, I think it is still extremely helpful if you can do this by mathematics. Okay, unless of course in terms of English, you are very clear about what you want to how you want to write things out. Okay, so the next thing we're going to do is we're going to do part B. So for part B, they said the hydrogen peroxide reacts with acidified iodide, liberating iodine. In investigations of this reaction, the following results were obtained. So you notice some of these results were obtained. You have initial concentration of the reactants, and then of course there are 3 reactants here: H plus, H2O2, and I minus. And then you have initial rate of formation of iodine as well. And then they ask which statements follow from these results. So again, you just need to pick the correct options. Okay, so yeah, I mean, we'll try. Okay, so so for the first 2, you notice that the concentration of iodide and H plus are kept a constant. And then you triple the concentration of H2O2. So this triples. And then you notice that your initial rate triples as well. So the order of reaction respect to H2O2 is actually 1. Okay, so this so there's no issue in this. Then the middle two double the concentration of iodide, the other two kept a constant. Okay, then you realize that your initial rate doubles as well, so therefore the order of reaction respect to iodide is actually 1 as well. Okay, then if you look at the last two, constant for H2O2, constant for I minus, H plus doubles, initial rate remains the same. Okay, so therefore it's zero order respect to H plus. So therefore statement 1 is correct because first order respect to H2O2, first order respect to iodide. Okay, then of course statement 2 is correct as well because zero order respect to the acids. Okay, and then shall we calculate the rate constant? Whether is it 0.2? Okay, so we can easily perform the calculation we can just do the first the first set of data. So 2.0 times 10 to the power minus 6. This is equals to K. H2O2 is 0.010 and I minus is 0.01 as well. And then H plus is to the power 1, so power 0, so that's fine. So that's 2.0 times 10 to the power minus 6 equals to K 10 to the power minus 4. So if I do a quick cancellation, you notice that the rate constant is actually 2.0 times 10 to the power minus 2 and not 2.0 times 10 to the power minus 1. So this is incorrect. So I'll choose option B. Okay, yep. Then finally, the part C, we have the table below shows experimental results. Okay, 2xO plus O2, you get 2xO2. So you have some arbitrary units of partial pressure. So let's try to do something about it. So, well, first two, we quadruples the concentration of O2, initial rate quadruples. So order of reaction with respect to oxygen is 1. Okay, so let's try for XO. So we increase the the partial pressure of XO from 50 to 100. We kept this a constant, and then relative rate doubles from 0.5 to 1. So also first order respect to XO. Okay, so now let's see. For this particular portion, we are keeping XO. We're keeping XO fixed at 50. The only thing that we change is the partial pressure of O2, and then you notice that the initial rates decreases by 4 times, right? Decreases by 4 times. Yeah, so because it's first order with respect to O2 and we are keeping XO fixed, so therefore I should decrease this by 4 times as well. So therefore I'll choose A, which is 25. Okay, yep. So I think we are pretty much done. The next part is just a summary. So I really urge you to if you still have some burning question, write them down and then ask me as and when you're able to do that, especially the pseudo nth order reactions, because you're going to see it appearing in the practicals over and over again. Okay, and then where possible, do a summary. I think we have this particular page. You are required to actually do a summary on the various graph. So over here, we have 3 sets of graph for you. Reactant time, product times, and rate against concentration or reactant. Again, I would like to emphasize to you that your role is not to memorize all this. Okay, please do not memorize the shape of the graph. Derive them as you go along the way. Okay, I think it helps a lot, especially in your practicals and your theory papers as well. Okay, yep.